It is a strangely specific rule in a lot of households. Like, you never, ever store leftover lemon pickle
Hmm.
or, sour curd in a brass or copper vessel.
Oh, yeah. That is a very classic rule.
Right. And if you grew up hearing that, you probably just assumed it was, well, a kitchen superstition, just one of those old wives' tales passed down to you.
Most people do, yeah.
But if you actually do it, you aren't just ruining your food. You're triggering an invisible chemical war zone right there on your countertop.
It is a very real, very physical reaction. You are essentially setting up this localized, corrosive environment.
Wow.
Yeah, the acids in the food actively strip the metal ions straight from the container. So you're turning a delicious snack into, well, a mild toxic hazard.
That is wild. Well, welcome to the deep dive. Today we are uncovering the hidden rules of acids, bases, and salts.
We have some fascinating sources to go through today.
We really do. Because that brass vessel rule, it proves that chemistry isn't just happening in, like, a sterile lab with beakers and safety goggles. It is an active tug-of-war happening all day, every day.
Exactly, in your kitchen, in the soil in your backyard, and even inside your own stomach.
So our mission today is to look past the basic textbook definitions you might remember from school. We want to explore the actual mechanics of these reactions for you.
Right, like how they impact your digestion or how they dictate the structural integrity of the food you eat.
Yeah, and how they keep your teeth from literally dissolving out of your head.
That's a big one. And what's fascinating here is the sheer scale of this constant balancing act.
How do you mean?
Well, it is a fundamental binary in nature. You have some substances constantly looking to give away certain ions, and others that are just desperate to take them in.
Like a microscopic transaction.
Exactly.
Yeah.
That exchange of microscopic currency basically dictates almost everything we interact with on a daily basis.
Okay, let's unpack this. Because the first practical hurdle with this binary is just identifying what we're actually dealing with, right?
Right, you have to know what's in front of you.
Yeah, and we know acids are generally sour, like lemon juice,
Mm.
and bases are, bitter, and they feel kind of soapy to the touch.
But obviously, tasting or touching mysterious chemicals is a terrible survival strategy for anyone.
Yeah, please don't do that. So we rely on indicators. They act like chemical lie detectors for us.
That's a great way to put it. They expose the true nature of a substance without us having to put ourselves in danger.
And the gold standard for this, the one we probably all used at some point in science class, is litmus paper.
Litmus is a total classic, but its origins are actually what make it really interesting.
Oh, really?
Yeah, we tend to treat it like a manufactured chemical tool, right? But it's actually a natural dye. It's extracted from lichen.
Wait, lichen? Like the stuff on rocks?
Yeah, specifically from plants belonging to the thallophyta division.
Wait, so our ultimate scientific diagnostic tool is basically just, like, purple plant juice.
Essentially, yes. When that lichen extract is in a perfectly neutral solution, it's just a standard purple color.
Okay.
But it contains this mixture of different dye molecules that are highly, highly sensitive to their chemical environment.
So they react to whatever they touch.
Right. When the environment shifts toward acidic, the actual molecular structure of the dye physically changes.
Oh, I see.
And that alters how it absorbs and reflects light, which makes it look red to our eyes. And in a basic environment, a different structural shift occurs, and it reflects blue.
That concept of molecular shape changing how light reflects makes so much sense when you think about turmeric.
Oh, the curry stain effect?
Yes. Anyone who has ever spilled chicken tikka masala on a white shirt knows this exact pain.
It is notoriously difficult to deal with.
You get that bright yellow curry stain, and your first instinct is to, like, scrub it with heavy-duty laundry soap.
Which is actually the worst thing you can do.
Right. Right. Because the second the soap hits it, the stain doesn't fade at all. It turns this terrifying, deep, reddish-brown color.
Which is a perfect real-world demonstration of an acid-base reaction happening right in your laundry room.
So what's actually happening to the shirt?
Well, turmeric contains a pigment called curcumin. Now, curcumin is naturally yellow in acidic or neutral environments, but soap is highly basic. It contains a lot of hydroxide ions.
So those hydroxide ions are physically attacking the curcumin.
Well, attacking might be a bit dramatic, but they are definitely interacting with it.
Fair enough.
The hydroxide ions from the basic soap actually pull a proton away from the curcumin molecule.
Just snatch it right off.
Exactly. And that single proton removal causes a cascade effect. It rearranges the double bonds within the curcumin molecule itself.
Oh, wow. So it literally changes shape.
Yes. And because its physical shape has changed, it absorbs different wavelengths of light, shifting its color from yellow to that deep red.
And the proof that it's just a structural change is that it's totally reversible, right?
Oh, precisely.
Like, if you panic and just blast that reddish-brown stain with a ton of water, washing all that basic soap away,
The curcumin just grabs a proton back from the water.
and it reverts right back to its original shape, and the stain goes right back to being yellow.
It's a reversible lie detector right on your shirt. Nature provides its own diagnostic tools right in our kitchens.
That is so cool. But beyond visual indicators like litmus or, synthetic ones like methyl orange or phenolphthalein, there are olfactory indicators.
Yes, ones you can smell.
And this is where I want to push back a bit, because the concept of an indicator you can smell seems almost paradoxical to me.
In what way?
Well, we're told things like finely chopped onions, clove oil, or vanilla essence change their odor depending on whether they are in an acidic or basic medium.
That's correct.
Wait, so if I put vanilla in a base, it acts like a chemical mute button, and the smell completely disappears.
It really does. The smell completely vanishes.
But my question is, are we destroying the vanilla molecule, or are we just hiding the scent?
That is a really great distinction to make. We aren't obliterating the molecule at all. We are just altering how it interfaces with human biology.
Okay, how does that work?
Well, your sense of smell relies on olfactory receptors up in your nose, and they operate on a very precise lock and key mechanism.
Right, like a puzzle piece.
Exactly. The vanillin molecule has a specific shape, the key that fits perfectly into certain receptors, the lock.
So my brain registers that specific fit as the smell of vanilla baking.
Correct. Now, when you introduce a strong base, like sodium hydroxide, it interacts with a specific part of the vanillin molecule called a phenol group.
Okay.
The base just plucks a hydrogen atom right off that group. Suddenly, the shape of the key has changed. It no longer fits into your olfactory receptors.
Oh my gosh.
The vanillin molecule is still sitting right there in the beaker, but because its shape is warped, your brain no longer receives the signal that says vanilla.
That is wild.
And interestingly, if you drop that same vanilla into hydrochloric acid, the acid doesn't strip that hydrogen atom. The shape stays perfectly intact, and you can still smell it.
So the base literally bends the key, so it can't open the door in your nose.
That's a perfect way to visualize it.
That is just wild. But I think it brings up a crucial transition point for us. We know how to detect these hidden chemical states now, but what actually triggers them?
Right, they don't just happen in a vacuum.
Exactly.
Yeah.
And acid isn't just perpetually burning everything around it. It needs a catalyst to wake it up. And that catalyst is water.
If we connect this to the bigger picture, water is really the great enabler of our chemical reality.
It's the spark.
Without it, the defining characteristics of acids and bases simply remain dormant. They can't do anything.
Let's look at the dry litmus experiment from our sources to prove that, because this really surprised me.
It's a very elegant experiment.
If you take dry hydrogen chloride gas, completely devoid of any moisture, and you pass it over a dry strip of blue litmus paper,
Yeah.
absolutely nothing happens.
Nothing at all.
The chemical lie detector is just silent. It only turns red if the litmus paper is wet.
And this goes to the very definition of what an acid actually is.
Yeah.
An acid is a substance that produces hydrogen ions H+,
Right.
and a base produces hydroxide ions OH-. But in that dry hydrogen chloride gas, the hydrogen atom is tightly bonded to the chlorine atom.
So they don't just split apart for no reason.
No, they don't. They absolutely need the water to break them up. And it's even more complex than just splitting them apart.
How so?
Well, a hydrogen ion is essentially just a naked proton. It is incredibly small, and it possesses an intensely concentrated positive charge.
Just pure charge.
Right. Because of that extreme charge density, it cannot exist freely on its own. It is way too unstable.
So it needs a partner.
Exactly. When water is introduced, that naked proton immediately latches onto a water molecule, and that forms what we call a hydronium ion H3O+.
So it's not the acid itself that does the work, it's the hydronium ion that gives the acid its corrosive acidic properties.
Precisely. Water is the vehicle that allows the acid to exist in an active state.
So without water, an acid is basically just potential energy waiting for a medium to act within.
That's exactly right.
Which makes the process of dilution incredibly dangerous, doesn't it? Because if water wakes the acid up, adding water to decrease the concentration of ions releases just a massive amount of energy.
The safety implications here are severe. The rule in a lab is absolute. You must always add acid to water slowly with constant stirring.
And never the other way around.
Never, ever add water to concentrated acid. The mixing of water and concentrated acid is highly exothermic. It releases a staggering amount of heat.
Here's where it gets really interesting. When you think about adding a few drops of water to a beaker of concentrated acid, it feels similar to a grease fire in a kitchen.
Oh, that's an interesting comparison.
Like if you throw a cup of water onto burning oil, the system violently rejects it and it explodes outward. It feels like the same kind of angry rejection.
I'd push back on that analogy just slightly, though it's close visually.
Okay, what's the difference?
Well, it's close in terms of the visual result, an explosion of material, but the physical mechanism is entirely different.
Oh, really?
Yeah. A grease fire is a runaway combustion reaction. But adding water to acid isn't combustion. It's an extreme physics problem involving rapid thermal expansion.
How so?
Think about heat capacity. Concentrated acid doesn't absorb heat well at all. So if you drop a small amount of water into a large pool of concentrated acid, the hydration reaction generates an enormous spike of heat locally, right where the water hit.
Oh, I see.
Because the surrounding acid can't absorb that heat, all of that energy transfers directly back into the water drop.
And water boils?
Instantly. It instantly boils and flashes into steam. And when water turns to steam, it expands to over 1,000 times its liquid volume in a fraction of a second.
Oh, wow. So that violent expansion acts like a tiny bomb going off right into the surface, blasting the concentrated acid outward in every direction.
Exactly. It causes severe chemical burns, and it can even shatter the glass container just from the localized thermal shock.
That is terrifying.
It is. But if you reverse the process, adding a few drops of acid into a large pool of water, the mechanics change completely.
Because there's more water.
Right, because water has an incredibly high specific heat capacity. It acts as a massive thermal sponge.
Okay.
As the acid drops in and generates heat, the large volume of water absorbs and safely dissipates that energy before anything can boil.
That completely reframes how I view a beaker of liquid. It's not just sitting there, it's like a loaded spring of potential energy.
It really is.
So, how do we actually quantify that hazard? We know water unleashes this power, but how do we measure just how aggressive a solution has become?
For that, we use the pH scale. It's a logarithmic scale used to specify the acidity or basicity of an aqueous solution.
Right.
The P in pH comes from the German word Potenz, meaning power. So it is literally a measure of the power of the hydrogen ion concentration.
And the scale goes from 0 to 14, right?
Yes. 0 is highly acidic, up to 14, which is highly alkaline or basic. And right in the middle, 7 is perfectly neutral.
And as an audience that generally follows science, we're familiar with the pH scale. But what I find stunning from our deep dive today is the extreme fragility of human biology within that scale.
It's remarkably narrow.
Yeah, our bodies only function within a pH range of 7.0 to 7.8. That is nothing.
It is an incredibly narrow window for survival. Living organisms have evolved to rely on highly specific enzyme reactions, and those enzymes denature or essentially lose their shape if the pH shifts even slightly out of bounds.
So if the shape changes, they stop working, just like the vanilla.
Exactly. And we see this fragility out in the environment too. When the pH of rainwater drops below 5.6, we classify it as acid rain.
Which is devastating.
It is. When that rain flows into rivers, it drastically lowers the pH of the water, and aquatic life simply asphyxiates or experiences metabolic failure because their chemical environment is no longer compatible with their biology.
You contrast that fragile terrestrial window with the rest of our solar system, and it's terrifying. Like, look at Venus.
Oh, Venus is a nightmare environment.
Its atmosphere is dominated by thick, opaque clouds made of sulfuric acid. Just planetary-scale weather systems of battery acid.
It's hard to even comprehend.
It is. But we don't even need to look to Venus to see acidity dismantling tough structures. It happens every single day inside our own mouths.
Yes. Tooth decay is perhaps the most universal example of acid corrosion we experience.
Right, and we all know sugar causes cavities, and brushing prevents them. But looking at the actual mechanism is fascinating.
It really is.
Because tooth enamel is made of calcium hydroxyapatite. This is a crystalline form of calcium phosphate, and it is the absolute hardest substance in the human body.
Harder than bone.
Yeah, it is designed to crush food for decades. It doesn't dissolve in water, it can withstand massive bite force, but it has this microscopic Achilles heel,
Its crystalline matrix is highly, highly vulnerable to hydrogen ions.
the naked protons again.
Exactly. When the pH in your mouth drops below exactly 5.5, the environment becomes acidic enough that the hydrogen ions begin to actively pull calcium and phosphate ions right out of the enamel structure.
So the acid is literally dismantling the crystal lattice of your teeth.
Piece by piece.
But what blew my mind in our research is that the sugar we eat isn't actually the acid.
No, it's not.
If I eat a ton of sugar, am I literally turning my mouth into an acid bath?
Not directly, no. The sugar is just the fuel supply. The actual threat is the bacteria living in your oral microbiome.
Oh, right, the plaque.
Yes. When you consume sugar, these bacteria feast on the remnants trapped between your teeth. And as they metabolize those carbohydrates, their waste product is lactic acid.
So they are essentially factor-producing acid right on the surface of the calcium hydroxyapatite.
Precisely. That localized acid production plummets the pH below that critical 5.5 threshold, and that initiates the demineralization.
That makes so much sense.
And this is exactly why toothpaste isn't just like a soap to scrub away food particles. Most toothpastes are basic in nature.
Oh, to fight the acid.
Yes. When you brush, you are introducing hydroxide ions into the environment to actively neutralize the bacterial acid. That halts the extraction of calcium and gives your enamel a chance to remineralize.
It's a literal chemical war in your mouth every night. But bacteria aren't the only ones using acid offensively. Nature has weaponized acidity for millions of years.
Oh, constantly.
If you've ever been stung by a honeybee, the intense throbbing pain isn't just from the physical puncture of the stinger. The bee is injecting an acidic liquid deep into your tissue.
And we see the botanical equivalent of this in the wild with the stinging nettle plant.
Oh, I hate those.
Right. The nettle has these specialized stinging hairs on its leaves. If you brush against it, those fragile silica hairs snap off, creating microscopic hypodermic needles.
Oh, that sounds awful.
And they inject methanoic acid right into your epidermis.
Which causes a severe burning sensation. But this is where nature gets incredibly poetic. If you find yourself stung by a nettle in the woods, the cure is almost always growing less than 3 feet away.
The dock plant.
Exactly, the dock plant.
This is a classic example of traditional remedies being rooted in hard chemistry, because the sap inside the leaves of the dock plant is chemically basic.
So if you crush the dock leaf and rub it over the nettle sting, the basic sap physically interacts with the methanoic acid in your skin.
Right, neutralizing it and stopping the pain.
Nature provides the poison and the cure side by side. It's beautiful, really.
It is a very elegant system.
Which leads to an inevitable question for us. What happens after that chemical battle is actually over? When the acid from the nettle and the base from the dock plant destroy each other, where does all that chemical energy and matter go?
Well, it doesn't just vanish. A neutralization reaction, an acid reacting with a base, always yields 2 specific products, water and a salt.
So what does this all mean? When we say salt, I feel like most people immediately picture the little shaker on their dining table.
Of course. That is sodium chloride, which is just one specific member of an enormous family of compounds.
Right.
In chemistry, a salt is simply any ionic compound formed by the neutralization of an acid and a base.
And sodium chloride common salt is undoubtedly the most famous one. It has literally driven human history.
Wars have been fought over it.
Yeah. Mahatma Gandhi's Dandi March utilized sodium chloride as a powerful symbol in the struggle for Indian independence.
It's deeply woven into society.
It really is.
Yeah.
But beyond politics and, seasoning fries, salt water is the foundation for one of the most aggressive and vital industrial processes on the planet, the chlor-alkali process.
The chlor-alkali process is a masterclass in forcing a non-spontaneous reaction.
What does that mean, non-spontaneous?
Well, left alone, salt water or brine is perfectly stable. It will just sit in a bucket forever without changing.
Right, it's just salty water.
But we want the elements locked inside those molecules. So to get them, we pass a powerful electrical current directly through the aqueous sodium chloride.
We are essentially zapping the salt water with enough electricity to violently tear apart the chemical bonds holding the sodium, chlorine, hydrogen, and oxygen together.
That's a good way to describe it. That electrical energy breaks the water and the salt molecules apart at the electrodes.
Okay, so what do we get out of it?
Well, the chloride ions are oxidized at the anode to form chlorine gas. The water molecules are reduced at the cathode to form hydrogen gas. And that leaves behind hydroxide ions, which pair with the sodium to create sodium hydroxide in the solution.
So we tear apart inert salt water. to create three incredibly potent volatile materials.
Very potent, yes.
Chlorine gas, which is used to manufacture PVC pipes, disinfectants, and CFCs. Hydrogen gas, which is a highly combustible fuel and critical for making ammonia for fertilizers. And sodium hydroxide, which is an industrial strength base used to manufacture paper and soap.
All of that economic power comes from just forcing electricity through salty water.
It's unbelievable. And common salt is also the fundamental raw material for producing another household staple, baking soda, or, scientifically, sodium hydrogen carbonate.
Yes, baking soda is fascinating.
Now, we all know baking soda makes bread and cakes rise. That's like day one culinary science. But the actual mechanism of how it does that completely changed how I view a bakery.
It's not just mixing ingredients.
No, it's a process of thermal decomposition.
Exactly. When you mix baking soda into a wet dough and expose it to the heat of an oven, the sodium hydrogen carbonate molecule physically breaks apart.
It fractures.
Right. The heat forces it to decompose into sodium carbonate, water, and crucially, carbon dioxide gas.
This is the part that fascinates me. Wait, so baking a cake is essentially trapping the gas of a chemical decomposition reaction so the bread blows up like a balloon.
That is exactly what you are doing.
That is amazing.
Baking a cake isn't just cooking a liquid into a solid. You are orchestrating a controlled chemical detonation.
Wow.
The sheet triggers the decomposition, the carbon dioxide gas rapidly expands, but because it's trapped inside the viscous web of gluten in the dough, the gas bubbles just push outward.
Like millions of tiny balloons.
Yes, they physically inflate the structure of the bread, giving it that soft, spongy texture. You are literally manipulating the physical architecture of your food using a gaseous byproduct.
Cooking is applied chemistry, man. It really is. But speaking of manipulating physical architecture, there is a concept regarding salts in our sources that challenges one of our most basic assumptions about the physical world.
Oh, the water of crystallization.
Yes, it forces us to ask, are the dry crystals we see actually dry?
This raises an important question about how we even define states of matter, because, common sense dictates that a solid crystal is, by definition, completely devoid of liquid water.
Right. If it's a solid powder or crystal, it's dry.
But common sense often fails us at the molecular level. Consider copper sulfate crystals.
Okay.
If you hold them in your hand, they appear as these beautiful, perfectly dry, deep blue geometric shapes. But if you place those dry crystals into a boiling tube and apply a flame, something really unexpected happens.
What happens?
Condensation, actual water droplets, starts forming on the upper, cooler glass of the tube. And simultaneously, the vibrant blue crystal collapses into a dull, stark white powder.
Where did the water come from? I mean, it wasn't wet to the touch.
It was hiding in plain sight. This is a phenomenon known as the water of crystallization.
That sounds like a fantasy novel term.
It really does. But these water molecules are not trapped in tiny liquid puddles inside the solid. They are fixed numbers of water molecules that are chemically bound to the metal ions within the crystal lattice itself.
Wait, so they act as actual structural building blocks?
Yes. Water is acting as a solid structural component. In the case of copper sulfate, every single unit of copper sulfate is bonded to exactly 5 water molecules.
That is mind-blowing.
Those specific coordinate bonds are what dictate the crystalline geometry in that brilliant blue color. When you apply heat, you provide enough kinetic energy to break those structural bonds.
And the water just evaporates away.
Exactly. The structural lattice collapses without it, and you are left with anhydrous copper sulfate, that white powder.
And if you let it cool and add a few drops of liquid water back into that white powder, it violently reabsorbs the moisture, the structural bonds reform, and the blue crystalline shape instantly returns.
Just like magic.
It is a massive paradigm shift in how I think about solids. But it's not just a cool party trick either, is it? We use this exact structural chemistry in medicine.
Yes, we do. You're referring to plaster of Paris.
Right. Doctors use this to set broken bones. And plaster of Paris is created from a salt called gypsum.
Gypsum is a great example.
Gypsum naturally has 2 molecules of water of crystallization built into its structure. If you heat gypsum in a kiln to exactly 373 Kelvin, it starts shedding that structural water.
It loses exactly 1.5 water molecules, leaving it as calcium sulfate hemihydrate.
Now, obviously, you cannot physically have half of a water molecule, right?
No, you can't split a molecule like that. It's written that way to indicate a ratio. It means 2 formula units of calcium sulfate are sharing a single molecule of water between them.
And that resulting thirsty white powder is plaster of Paris.
Precisely.
When a doctor wraps your broken arm, they mix that powder with water. The powder eagerly grabs those missing water molecules right out of the liquid and chemically snaps back into the dense, solid, crystalline structure of gypsum.
It hardens almost immediately.
Right, creating this immovable cast that holds the fractured bone in place while your body heals. We are literally using the geometric rigidity of hidden water molecules to repair human skeletons.
It's incredible, and it ties everything we've discussed today together perfectly. It shows how profoundly these invisible chemical interactions shape our tangible reality.
It really does. So let's trace the thread of what we've unpacked for you today. We started by understanding that a curry stain turning red isn't magic. It's a basic soap physically shifting the molecular structure of turmeric.
Right.
We realize that acids are completely dormant until the catalyst of water allows them to form aggressive hydronium ions.
The naked protons in action.
Yeah. We explored the thermodynamic violence of diluting those acids incorrectly. We looked at how a tiny drop in pH can dismantle the hardest crystal in the human body, your teeth.
And how the dock plant chemically neutralizes the biological warfare of the stinging metal.
Yes. And finally, how the hidden structural water inside a dry crystal can be used to set a broken bone.
It's a reminder that we don't just observe chemistry, we actually live inside it.
Very true.
And I'd like to leave you with one final thought that builds on these concepts we've explored.
Oh, please do.
We discussed the chlor-alkali process earlier, right? The industrial mechanism of taking ordinary salt water and tearing it apart with electricity to produce chlorine and, crucially, hydrogen gas.
Yeah, tearing the water apart.
Now, hydrogen is currently one of the most sought-after clean fuels for the future of human energy. So consider the fact that our planet is covered by vast, impossibly deep oceans of salt water.
Oh, I see where you're going with this.
The next time you stand on a beach and look out at the water, ask yourself, are you just looking at the ocean, or are you looking at the largest untapped battery of chemical energy on Earth, just waiting for the right electrical reaction to unlock it?
Wow, that completely changes the view from the shoreline for me.
Yep.
Well, thank you so much for joining us on this deep dive. The next time you brush your teeth or bake a cake or look at a brass vessel sitting on your kitchen counter, we hope you see the invisible chemical tug of war that is constantly balancing the world around you. Keep questioning, keep learning, and we'll catch you on the next one.